Okay. So one thing we're going to do a lot in this class later on is look at those 95% confidence intervals, because they come up in science and in like studies all over the place. And don't write this down, but just pay attention. What those 95% confidence intervals tell you says that the true mean is in 95% of the CIs you find. So this comes up, there are confidence intervals that you're given for things like election polling, as in candidate blah, we'll pick Gary Johnson because he's not going to elicit any strong response from anybody. Candidate Gary Johnson polls at this number with this margin of error, which means if you repeatedly do this experiment, the true people who support him is going to fall within those intervals that much percent of the time, okay? So what we need to talk about probability for is to talk about, okay, well, how unlikely is it that the true mean will not fall in that interval? That'll happen 5% of the time, right? So that's what those confidence intervals mean, is that most of the time they're going to have your true proportion, but sometimes they won't. Okay. So the first thing, called random circumstances. So we're talking about statistics. It's a collection of procedures and principles for gathering data and analyzing information to help make decisions when faced with uncertainty. So we're going to use blank to talk about events that are uncertain. So we're going to use probabilities. So something is called a circumstance in which the outcome is unpredictable. The outcome is not determined until it is observed. This is called a random circumstance. So for example, what side will a coin come up when you flip it? You don't know what it is until you actually do it, right? What's the dice going to be when you roll the dice? What's your grade going to be in this class? That's kind of a random circumstance too, right? Although with some control. Okay, so probabilities, have you seen them before, like a little bit? Okay, so what are they in between? So probability, it's a number between what and what? 0 and 1. 0 meaning the event never happens, 1 meaning it always happens. So probability of blank means an event is impossible, that's 0. Probability of blank means it always happens. An example of an impossible event. Throw a die and roll a 7. That's never going to happen, right? You can, unless it's a standard die who has size 1 through 6. Yeah, okay, so we're not going to do a funky die. A regular die, 6 size, numbered 1 through 6, you will not roll a 7. Flip a coin and get a chicken. Okay, that's not going to happen either, right? Probability of 1 means it always happens. Flip a coin and get heads or tails. You always get one or the other, assuming coins don't land on their sides and stay that way, because they usually don't. Okay. Yeah?
I have a question. So in that example, because flip the coin has landed on its side at some point for
yeah,
somebody,
perhaps that's not a great one. So let's say a certain event is rolling a 1, 2, 3, 4, 5, or 6 on a die.
No, I just mean what would, between 0 and 1, what would landing on your side be?
Oh, I think that a possibility is completely discarded from that theory. You can also use probabilities to describe events like what's the chances your flight's going to be on time. So according to the U.S. Department of Transportation, 78.7% of domestic flights in the top 18 airlines arrived on time in January 2010. So represent this random circumstance and give in terms of a probability. So what's the probability that your flight is going to be on time? Yep, percents really are out of 100, right? So it's really 78.7 out of 100, which is 0.787. So what about probability of not on time? What would that be? Yeah, 1 minus that. either you're on time or you're not, right? And if 78% of flights are on time, then 31.3% are not, right? Does that make sense? So that would be 0.313. If you wanted to be more fancy.
Wouldn't that be 213?
Oh, so yes. Did I mention I was up until 2 in the morning grading your tests? This might be because I'm tired. Oh, I did it again. I hate it when I do that. Oh, 0.213. Yes, thank you. Okay. So your book makes this little distinction between random circumstances in which the outcome isn't determined until we observe it, and the second one is the outcome is determined, but our knowledge of it is uncertain. So, I don't know which one's easier, but let's do them on the same slide because I think the distinction makes sense. So let's do part B first. The outcome is determined, but you don't know what's going to happen. So one of the examples the book gave is the numbers on a scratch-off ticket, scratch-off lottery ticket. When you buy that ticket, the numbers are already there, and whether or not you win's already been determined, but you don't know until you actually scratch off the numbers.
Could pregnancy work there?
That was my example, actually. You know, up to a point in a pregnancy, the gender of your baby, it's already been decided. You just don't know what it is, right? So, okay. The outcome is not determined until we observe it. So this could be something like a Powerball type lottery. Do we have those? We don't have lottery. Do we have lottery in Alaska? Oh. Okay. But you know what Powerball, how that works? Like put balls in thing and they draw them out. And so, yeah, I guess bingo also could be like this. But what they do is they put that's kind of like bingo. They put like little like ping pong balls with numbers on them in a thing and they roll them around and they draw balls out of there. And then they like decide on the spot what the numbers are. Unlike a ticket where it's scratch off where the number has been decided and the tickets went out.
Did people buy tickets with numbers?
People buy tickets, I think they actually pick the numbers usually.
You can, or you can rent.
Or sometimes, yeah, so I've never played because I know the probability of winning is super low.
Probably winning never playing is
Oh,
ultra low.
there are really cool applications and examples of people who have gamed lottery systems. And we're going to learn something in this class called expected value, which will help us figure out like how these people were able to game these lottery systems and come out ahead. It's kind of neat. So I'll bring those examples into class when it makes sense because they're really fun. And they actually kind of like shut the lottery down because they won money from it. Anyhow, it's because they bought a lot of tickets.
So the Nina and Ice class would be like a grade. That would be not
Mhm.
determined.
Yeah, the Nina Ice Classic is also an example. Do you guys know what that is? Where they put the pole
flag
and
drop.
put the pole on the river, and you guess what date and time the river's going to go out.
Well, know what time the flag drops.
Time the flag drops and
Yeah.
the ice goes out.
Yeah.
Allegedly, the ice goes
Yeah,
out.
it drops into the water and the bell rings.
Uh-huh.
So it has to ring.
Yeah, it's a thing. It's an Alaska thing. It's the Alaska's lottery. Okay,
It's really fun.
it's pretty fun. I've never played that either.
The last movie, a lot of people actually use the science to figure out when it's going to drop.
Yeah.
Yeah,
It's
yeah.
not just luck.
That's not just luck. No. Okay, are these following values legitimate probabilities? Yes or no? First one?
Yes.
Yes. Second one?
Yes.
Yes. Third one? No. Last one? No. And the explanation is that it must be, let's do this. P is in between 0 and 1. Have you guys seen that notation before? The inequalities? The alligator's eating towards the bigger numbers, right? The littlest number is 0, the biggest one is 1. Did you guys learn? Okay, so sorry. Love the alligator analogy.
It's the most creative analogy I've heard.
It's great. Have you heard it before?
Never heard of
Not
it?
the alligator.
Really? Oh, it's,
always go for the bigger number.
yeah, it's the hungry alligator.
The arrow points towards the smallest one.
The arrow points to the smallest one, yeah, but the alligator's eating the big one.
The bigger number.
Alligator's mouth
Mhm.
is
You're such a
the bigger
realist.
number.
Okay, so for certain things we talk about probability, things like tossing a coin, you can think, okay, both sides are equally likely, and therefore it probably is, half for heads, half for tails. Same thing for dice, right? But for certain things like what is the chances that you're going to pass Beth's statistics class? It isn't like it's always 50-50, right? And God, hopefully it's not, because that would be terrible. But it could be the case that I could look at my statistics classes over a long time and take the people who passed divided by the total number of people who took my class, right? That's called the relative frequency interpretation. So this applies to situations in which you can envision repeatedly observing the results. So for me, repeatedly observing how many students passed my class. That's called the relative frequency distribution. People have done this with coins. Like they've taken coins and flipped them like thousands of times to see if it actually comes out to being like half and half for both heads and tails. That's what it is. You repeatedly observe the experiment. And for some things, this makes total sense. Like your risk of dying in a plane crash is this, right? Number of plane crashes divided by how many flights there have been. It's quite low. So, feel bad. Okay. So suppose you live in a city that has 125,000 households and a polling agency selects 1,000 of them to contact for a survey. So express this fact as a proportion, percent, and probability. So what is the proportion? The proportion is the 1,000 over 125,000, right? Did you guys learn about canceling zeros in like elementary school? Okay. So I think this cancels to 1 over 125.
Yep.
Okay. Canceling zeros works because you could divide by 10 repeatedly, right? That's why. As a decimal, this is 0.008. All right, so what is that as a percent? 0.8%. You don't need the 0 point, it's just a pet peeve of mine, I put it there. How about the probability? It's already up there. It's 0.008. The probability is just the percent in decimal form. That's the same thing. That's all that's pointing out. Okay, so determining the relative frequency probability of an outcome. So there are two ways to do this. Method one is to make an assumption about the physical world. So for example, assume that having a boy and girl are equally likely, and so you have a 50-50 chance of either sex. That's actually not true in the long run, I think. I think there's a higher proportion of boys born, actually, a little bit. Or for example, you could assume a coin is fair. And both heads and tails are equally likely. This is a random thought that I just had right now. Do you know why it's called tails? Because it isn't like there's a tail on the backside of the coin.
What's the end of it?
Yeah, maybe it's just like there's a head and the other side of the head's the tail. I don't know, but like on an animal, head, tail. Okay. Now, method two is you could observe the relative frequency. This is like my example about this class. So, for example, the probability of passing Stat 200 would be equal to the number who passed divided by what? Total number of students, yep. And if I do a bigger and bigger sample, like I suppose I teach at UAF for like 10 years, and I have a large sample, then that's going to probably converge to what the actual thing is. Okay. So there's a fair amount of vocabulary you have to talk about with probability, and it's just good to be familiar with these words. So a simple event is a unique possible outcome of a random circumstance. Simple event. So, for example, if you toss a die, the simple events are getting a 1, 2, 3, 4, 5, and 6. A non-simple event would be like getting a 1 or a 2. But the simple is like just getting 1, just getting 2, just getting 3, just one thing at a time. Okay. Collection of all possible simple events, that's called the sample space. So it includes all possible things. If you toss your die, those are the possible events that could happen. No 7 in there, right? No 0. Yeah.
I still don't really understand the simple event. A unique possible outcome.
Like one's an event.
Like getting the 1, 2, 3, 4, 5, 6 in a row.
Nope. Like if you toss a die, let's just erase the event that you get a simple event is that you get 1. Like getting a 1 is a simple event. Getting a 2 is a different simple event. Getting a 3 is another simple event, but there's just one possible thing. An example of a non-simple event would be like the event of getting a 1 or a 2, because it contains 2 things in it. Because you can talk about the chances of that, right? You roll a die, I need a 1 or 2 to win the game.
Okay.
What's the chance I'm going to get 1 or 2? That's not simple anymore. But just getting a 1 is simple. And then the sample space is all the possible, like, simple individual events you can have. So you can think about simple as also being like an individual thing. When you put all those individual things together, you get all the possibilities. Okay, a compound event is an event that contains more than one simple event. So we're going to often use capital letters for events. So the event A could be getting a 1 or 2. If you roll a die, the compound event is either I get 1 or I get 2, or 1, 2, or 3, or an even number, right? That would also be a non-simple event. And just a general event is a collection of one or more simple events in the sample space. So that event thing encompasses both simple and compound events. Okay. So we already discussed this, but we can say it again. What are probabilities between? So that one we already had. Now, the sum of probabilities over all simple events, so every possible thing you can have happen, what does it have to be? 1. So kind of like if you roll your die, probability you get 1 is a 6, 2 is a 6, 3 is a 6, 4 is a 6, 5 is a 6, 6 is a 6. And once you've encompassed all possibilities, that adds up to everything has probability 1. Okay. Now, that's okay, as long as it's not at me. So if you have k equally likely simple events, so think about k as being like 6. If you roll a die, what's the chances you're going to get a 1? 1 out of 6, right? If I tossed a 20-sided coin, or 20-sided die, it'd be 1 out of 20. There are various games that have die that are like weird shapes and they've got lots of sides, right? Dungeons and Dragons? I haven't played that game. So if you have k equally likely events, the probability is 1 over k for each event. So for example, if you roll a die and record the number that appears, there are how many simple events? 6. Does that make sense? And what's the probability for each? 1 over 6. So here's the basic idea. When you're looking for probabilities, here's your basic starting point. The first thing you should do is figure out how many events are in your sample space, and then figure out how many events meet your given criteria. There's like a little bitty box of white space to the right of this. Let's do a really easy one, then we'll get to the next one, which is a teensy bit harder, okay? So for example, suppose we'll just go with roll a die. let A be the event that you get an even number, okay? What's the probability of that thing happening?
3 to 6.
There are 3 even numbers out of 6 total, right? Which is a half, right? Okay. Suppose that a lottery number is a 3-digit number between 3 zeros and 3 nines. What's the probability that the last digit is a 9, or that all 3 digits are the same? Okay, so first of all, what is the total number of things in sample space? As in, how many possible different lottery numbers are listed there?
900.
You're really close. It's actually 1,000.
Counting 0.
Because counting the 0, 0, 0. Okay, so how many of them have last digit 9? So let me backtrack for just a moment. Let's talk about another way to find the 1,000 other than just knowing that there's 1,000 things. You can think about it like you have 3 choices for numbers. You have the first number, second number, third number, right? How many numbers can you pick for the first number? 10, because 0 to 9, right? And then how many can you pick for the second number? 10. And then how many for the third number? Also 10. And you multiply those, and that gives you all the possible outcomes. And you can think like you have the possibilities that are 1 through 10, and then 1 and 1 through 10. And then of those, you gotta also add like another 1 through 10 to all of them. But what I think about is a little bit of a tree branching. I have 10 possibilities, and then of each of those comes 10 things, and then off each of those comes 10 more things. Ends up being 10 times 10 times 10, but the visual gets too big to draw. So we can think about the number of things in this event the same way. So if your last digit is 9, what can the first digit be? How many different things could it be? 10, anything, right? The second one could be 10. And the last one has to be 9, so how many choices do you have? 1. So the probability of last equals 9 is 10 times 10, or 100, over 1,000, which is, I think that's 1/10, right? Or 0.1. I don't care if you leave them as fractions or decimals, but it might be easier for your grader if you always put both. Because then whatever answer key I have it in, she'll be able to. Okay, all 3 digits are the same. Okay, so is the total number of things in the sample space any different? No, okay, so there's still 1,000 things in sample space. Okay. All the same. So how many numbers can you pick for the first slot? Then how many numbers can you pick for the next slot? 1. Yeah. So the thing is, like, I can also explain this with like listing all the possible outcomes. If you pick your first number as 2, what's your next number have to be? 2. First number is 5, next number must be 5. So once you pick that first number, the second one has to be the same. That's why this is just 10. So the probability of all same is 10 out of 1,000. What does that reduce to? 1 out of 100, or 0.01. Yep, exactly. With this one, you can probably also list all the possibilities of them all being the same and convince yourself there are only 10 of them. Like they are 0, 0, 0, right? 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, up to 9, 9, 9, right? And there are 10 different things there as well. So what you could do to confirm that your multiplication rule thing is correct You could do it that way. This first one, listing 100 things that way, was gonna be super tedious, right? As in, not gonna go there. Okay. So 2 events are called complementary events if they do not contain any of the same simple events and they together cover the whole sample space. Okay, so for example, with a coin, if I have heads is 1, what's the complement of heads? Tails. Assuming no, it's not possible to, get a coin on its side. The example we had with the airlines, right? Either your flight's on time or it's not, right? So being on time was one event, not on time was its complement. The notation for complement is A with a little superscript of C. Tells you what event it's related to and what event is the complement of. Also, P of A plus P of C has to equal what? 1. Have you guys seen Venn diagrams before? Yes. Okay, so here's a Venn diagram of that. So the box is my sample space. There's all the things that are in my event A. A complement is all the stuff outside of it, right? It doesn't need to be a squiggly box. It can be like, whatever. But the bubble contains everything. Either you're in A or you're in A complement. You're never in both. Okay. So suppose you have that lottery, described in example 5. It's you pick a number between 3 zeros and 3 nines. What's the chances that you're going to win? 1 in 1,000. There's one winning ticket out of 1,000 possibilities. Assuming there is one winning ticket, that is. I didn't say that, but we'll pretend there's one winning ticket. How about not winning? As the opposite of this event, right, or the complement. The probability of not win will be 1 minus 1 over 1,000, which somebody said was 999 over 1,000, right? Okay. And as decimals, that would be 0.001 and 0.999. How many numbers do lottery things usually have? 4 or 5? And they're also often 2-digit numbers, aren't they? Yeah. That's why I don't play the lottery.
0 to 49.
Yeah, it's kind of crazy. So do you get that complementary events can have nothing in common, and together they make up every possibility? Okay. Like with a die, complementary events could be rolling an even or rolling an odd, right? Because there's no overlap, but together they make up the whole sample space. Now, you also could have events that don't have anything in common, but they don't make the whole sample space. That's called mutually exclusive. So they do not contain any of the same simple events, but they do not need to cover the entire sample space. So for my Venn diagram, like here's my event A, there's my event B. They have nothing in common, but they don't make up the whole sample space, which is the box. And the whole do not need to, it's okay if they still do. Okay. So suppose you roll a 6-sided die. Give examples of events that are complementary. So I'm going to call them event A and event B. Just like list what's in them. So pick what you want.
Even and odd.
Yep, even and odd. That's one example. Your event A could also be roll a 1. What would event B have to be in that case?
Roll
2, 3, 4, 5, or 6. Anyhow, they can cover the whole sample space. How about mutually exclusive? So it's something that doesn't cover the whole sample space.
A is 2, B is 4.
Yep. So event A is rolling a 2, event B is rolling a 4. That's one possibility. Or how about this one? A is even and B is equal to 5. Does that seem? Okay. So suppose, again, we have that whole 3-digit lottery described in example 5. Are the events A, all the digits the same, and B, the first and last digits are different? Are these events complementary? So do they cover the whole sample space? So no. How about you give me an example of something that's not covered? So the first and last digits are different. So about 1, 2, 3, 1. Is that event covered in A? No. Is that event covered in B? No. So this is in neither.
It's also a 4-digit number, and it's 3 digits.
Oh, okay, well,
Second.
1, 2, 1 then, how's that? Yep, thank you, that's right, it was a three-digit lottery. So if you're trying to establish that events are complementary, you have to give me an example of something that's not in both of those. Does that make sense? Okay. So it's not in, this is in neither, thus this, or let's say these two events are not the whole sample space. Are they mutually exclusive? As in, can you, so you would be not mutually exclusive if you could be in both at the same time. So can you have all digits being the same and the first and last being different? No. So you can't be in both. Thus, these events are mutually exclusive. So I think you were right when you were nodding your head. So no, you cannot be in both, therefore they're mutually exclusive, right? Okay. A couple more vocabulary words. So 2 events are called independent of each other. If knowing one will occur does not change the chances of the other. So, for example, drawing a card from a deck and flipping a coin. As in, drawing the card from the deck does not affect the flipping the coin at all. Now, this is the intuitive definition, and I will say that the intuitive definition often fails people. There is another way to make this into a definition using probabilities, and we're going to have you rely on that more often once we get to it. But independent basically means that they do not affect each other at all. And the opposite of that is dependent. And that's if knowing one event will occur will change the outcome of the other. So, for example, drawing 2 cards from a deck. I'm going to add some words without replacement. That's how most cards work, right? If you're playing a card game, usually you take a card and take another card, right? You don't take a card and put it back. Not usually.
And is that because the
Because-
chance of you drawing that exact same card again or?
It would be 0, right? Yeah. Or even the other thing that changes is the number of cards you have to draw from changes as well, right? Because if you've taken out a card, instead of it being 52, now it's 51. So yeah, so what happens on your first draw will affect what happens on your second draw. Like once you draw the ace of hearts, you cannot draw it again, right? If you put the card back, then it's independent assuming that they were well mixed and stuff like that. I think that's the question, right? Suppose you are 2 cards from a deck. When are these events independent and when are they dependent? So they're independent if you put the card back. And we're going to also say that you mix or shuffle well. And this is called with replacement. When would these events be dependent? If you do what with the card? If you, yeah, don't put card back or keep card out. Okay. So remember that the event A with the superscript of C is the complement of the event A. Are the events A and A complement mutually exclusive?
No.
I think they actually are. So yes, because mutually exclusive just means they have nothing in common. They don't have to cover the whole sample space, but they can. Does that make sense? It's kind of like the relationship that rectangle, so rectangles are here, and inside of all the rectangles live the squares, right? Does that make sense? That's the relationship. Every square is a rectangle, but not vice versa.
But it says if the two events are called complementary events if they do not contain any of the same simple elements and together they cover the whole sample space.
So you can have a square and a rectangle.
Yeah, that's why.
Did I not edit need to? I think that I made a typo. Let me pause this. Been people who flip coins and done long run probabilities figure out like actually how much that is true.
Yeah, I know, they have.
Yeah.
It's like they did this thing.
Yeah.
If it was heavier, wouldn't it fall face down more often?
I'm sorry, you're right.
Tails.
It's more often than
So
they
I
do.
am now really confused because of this.
Well, not all of this is this specifically,
Yeah,
right?
no, just between complementary
And mutually
and mutually
exclusive.
exclusive, because we said that
Mutually exclusive means that they have nothing in common.
yes.
Complementary
Understand
means that they have nothing in common and they make the whole sample space.
that. But then wouldn't they not be mutually exclusive? Or
If they have nothing in common and they have this extra condition of including the whole sample space, they still have nothing in common.
okay,
Mutually exclusive only requires nothing in common.
okay.
That's all.
So they could have nothing in common and still cover.
The sample space and that means they're mutually exclusive.
Okay.
But they're also especially complementary.
And then I have a couple of questions on here. Were you just confused if that was a 1 or a 2?
I couldn't tell, so I assumed it was a 1.
Yeah.
I just can't see. It's
'Cause I
supposed to be a
got-
2. It has to round up.
I did round up
No, you didn't. I'm positive.
because that's what I got, and so it rounds up.
That's
to,
because you weren't specific enough.
Okay.
So it's a rounding this
Okay,
answer
so that
made
was a
that one
rounding error.
inaccurate. Yep.
Okay.
So that's
And
I couldn't
then-
tell that from your work. Yep.
For this one, that's the number I got when I did.
That was one of
30.
those. I guess I can give you credit for that because I couldn't tell if it was a 3 or a 1 again. Like I just
Okay,
didn't
that's
know.
a 1. Yeah.
Yeah, see what I'm
Okay,
saying?
I'm
That was
sorry.
definitely, I just couldn't tell what it was.
Okay.
I thought it was a 3, that's why I wrote 23.28. I just didn't
Okay.
know.
Okay, because I was like, that's the number I got was 21.
Yeah. I
Okay.
just couldn't, and I guess I could have looked here to see that was a 1. I just couldn't tell what you had written.
Okay.
Yeah, that's my
only
bad.
questions.
Okay.
This one you said it was 55?
Yeah.
So did I just because it wasn't marked wrong, so.
Oh, well, you got a gimme. Lucky you.
I was making sure.
Yeah, it's supposed to be 55. Okay,
I'm
yeah,
just curious, how come I got 2 out of 3?
because you
It's the
have to
same.
round up.
Okay.
Because
but
it
was
has to
all
be a whole
ones.
number. That's because the N is the sample size and it has to be a whole number.
Well, what if they were using like milligrams of a certain substance to test how different things reacted with
You
that?
still would take a whole number of samples.
Okay, okay.
It's
so
like
it
the
wouldn't be
number,
like-
it's the number of like test tubes you have or the number of people
Right.
you have. So it'll be, you wouldn't have half of a,
Okay, so that's what
it's
I
not
thought.
an
I just
amount,
wanted to-
it's like, it has to be an integer is kind
Okay.
of one of the requirements.
Okey-doke. Thank you.
Uh-huh.
I didn't, do you have my exam?
I didn't put it in there?
No.
Did I put it in the wrong folder?